Okay, so today we are going to talk about the squeeze theorem. And this is just one more tool to help us figure out special limits that really don't work for algebraic techniques. And actually, this is one of the tools that can be used to prove that sine of x over x is equal to 1. The limit as x approaches 0 of that. So let's just jump straight into it. So the squeeze theorem says that if we have an open interval around C, and we've got this set of three functions, basically we get this statement. I honestly think it's just a lot to take in, so I think it's almost better to use a picture to try to understand it. And it's kind of in the name. That's why it's called the squeeze theorem. So really we've got three functions. We've got a lower function, an upper function, and a function in between. So in this particular example, the blue function that you see down here is our lower function. The red function up here is our upper function, and then f of x is the function that lies between them. And the idea is that we have some open interval around x equals c. So in this case, that's going to be our c. Again, we can define our interval however we want, just as long as c is contained in it. And we've got a couple of conditions. Inside that interval that I've just made, we need to make sure that the upper function is bigger than the function of interest, f of x, and then that function is bigger than the lower function, just like we have in this picture here. And this needs to hold for every value of x. For those who haven't seen this before, that symbol just means for all. Okay, this of course means in, so we're talking about every value of x that's on this interval, except perhaps at c. So f of x can be undefined at c, or u of x or L of x. They don't necessarily have to be defined at c either. This can be, who knows what's happening at that point. But at every point in some interval around it, we need that to be the case. So what does the squeeze theorem say? Well, it says that if the limit of the the bottom function, this L of x, is the same as the limit of u of x at the point x equals c, as x approaches that value, okay, then by necessity, the middle function here will also have that same limit. So the way you want to think about this is you have an upper function, you have a lower function, and your function f of x is being squeezed between those two functions at the point x equals c, which in this case is 0, but it doesn't have to be 0. And if that's the case, it basically forces the inside function to have the same limit as the upper and lower limit. Okay, so that's great. And so the next question that we naturally need to ask is, well, how is this practically applied to help us find limits? Well, let's do an example to help us figure this out. So the example I want to look at is the function. So this is basically our f of x. That's the function of interest. And I want to find the limit as x approaches 0 of this particular thing. So, of course, like always, we should always try to do substitution to see what happens. We get 0 squared, we get the cosine of 1 over 0, and quite clearly we have this issue of dividing by 0. So this isn't going to work. Okay, that's not going to help us. We can't really factor, we can't really cancel. There's really not a whole lot we can do directly here. Okay, but we can use the squeeze theorem. Okay, and the idea is that we want to set up this kind of inequality. We've got a lower function, we've got our function of interest, and we have to find an upper function. So we need to find two functions that make this thing work. And the one thing that's really, really nice about trig functions, especially sine and cosine, is that there's already a built-in inequality about sine and cosine. So I know that sine of any function, of any value, always has to be between -1 and 1, because the sine value corresponds to the y value on the unit circle. And of course, the unit circle has a radius of 1, so it's impossible to get any value that is bigger than 1 or smaller than -1. And the same holds true for cosine. Now, the one thing to keep in mind here is that this is completely independent of our thetas, or we can even use the upside down a for all theta in the real numbers. Doesn't matter, okay? So it can be theta, it can be 1 over x. So I know that the cosine of 1 over x has to be between 1 and negative 1. And you actually see here that the cosine of 1 over x is almost part of this whole thing. And anytime we have an inequality like this, we can actually simply multiply all three parts of the inequality by x squared. And when we do this, we get this inequality, that x squared is going to be negative x squared, x squared times cosine of 1 over x will be between negative x squared and positive x squared. And this is actually true for all real numbers. This does not have to be true for all real numbers to satisfy the squeeze theorem, just as long as it's true for some interval around 0. And because it's true for all real numbers, it works. Actually, the only place it's not true is at 0, because we know that this is undefined at 0, which is fine. That meets the conditions of the squeeze theorem. So we now have a lower function here, and we have an upper function. So to apply the squeeze theorem, what we need to do is we need to find the limit as x approaches 0 of our bottom function. So this is L of x. And if we do that, just by substitution, we get 0. If I find the limit as x approaches 0 of positive x squared, that's our upper function, that's also 0. So the squeeze theorem concludes, because we've met all the conditions of the squeeze theorem, we can conclude that our original limit must also be equal to 0. So this is, again, a nice rigorous way to show that that's true. And if we actually go through the process of graphing this thing, this is, of course, y equals x squared. This is y equals negative x squared. And we see that our function of interest, which is the x squared times cosine of 1 over x, is actually getting squeezed between the two. And we see that the limit at 0 is going to be 0. So this is the squeeze theorem and how it is applied to an example. As always, I hope this helps, and take care.